So I posted the grades, obviously, yesterday, and so I also, updated all the average, but I also put up that other information about what you need for an A, B, and C. So that's your total grade on test 4 with the homework factored in. So like I said in the announcement, if you do the homework, it's, 18 less points, basically. So if you need like 100 to get an A, but if you do the homework, you get 18 points, so you really need like an 82 out of whatever it is, how many points the test will be to get an A. So the point is, make sure you do the homework if you need, significant amount of points to get whatever grade you want to get on for the class. The other thing is that I've only dropped one quiz, but there's 2 quizzes dropped. And there's going to be another quiz on Saturday before the test. So if you do better on the quiz, then your second lowest quiz grade to this point, and then your quiz average goes up, which would actually then also lower what you need on test 4 to get whatever grade you need, right? So what is on Canvas now is sort of a worst case scenario to get the grade that you need. But it is, so it's approximate in a couple of senses. One is that, your final quiz average isn't done yet. So, it's, I just went over that. It's not really, it changes a bit depending on what you get in your last quiz. It also changes a bit so the way I have it calculated now is whatever, how your test and quiz scores are related to one another. In other words, if right now your test score is higher than your quiz score, I calculate your average one way, and then if it's vice versa, I calculate it the other way. But if you do, suppose right now your quiz average is higher than your test average, and then you do really well in the last test, and then your test average becomes higher than your quiz average. Well, that kind of changes how everything works, right? Because, see what I'm saying? Like the weighting changes. So in that sense, it would be, a different score what you need if you were to change your relative average between your test and quiz average, right? So it is, in some sense, sort of approximate, but it's pretty accurate. So it should be within 5 to 10 points what you need to get on test 4, right? So it gives you an idea at least, right? But of course, you should get higher than what you need, right? If it says you need a 70 or something on test 4, then don't try to get a 70. Try to get higher than a 70 just to play safe. But anyhow, that's how it's going to work. So what we're doing this week is extra credit on the test. So like I said a few times, the test will have more than 110 points on it. So a typical test is 110 if you get a perfect score. This one will have more than 110. I don't know quite how many right now, but more than 110, let's just say that. So it's another thing. If you need a 70 on, let's just say you need a 70 to get an A. Well, if you do the extra credit, it's really like a 52. And then if you do well in the last quiz, it's less than a 52 because it could change your quiz average and maybe make it a 40-something. And then you really only need 40 out of more than 110 points, right? So there's all sorts of extra points at the end of the semester to hopefully get your grade higher than what it is. Does anyone have any questions on that so far? The grades or anything? Tomorrow there will be a review session. If anyone has any last minute questions on the homework, no one does. It's fine because the main review session for the homework was last Wednesday when we went over all of them step by step. So if no one shows up, it's okay. Or if people have a couple quick questions, I might not even record it if they're quick. If people have general questions that might help everyone else, then I might record it, but it might not even be recorded. But it's not a big deal because, like I said, the whole review session was up from last week anyhow. And then next Wednesday is going to be a review for the test, and next Tuesday we're going to review for the test, and I'm going to put the equation sheet up either tomorrow or Thursday for the test. You're going to have a quiz on Saturday for the test as well, and then of course the test is Thursday. And for those taking the final, I don't think there's that many people that are going to take the final. There aren't that many people actually that are in a position where they really need to take the final, but there are a few. I'm going to post information for the final starting sometime next week, but for most people, it doesn't really matter. So It's not a big deal, but I will post information regarding the final next week. But for now, don't worry about it. Okay, so does anyone have any questions on that? Okay, so today's lecture is going to be a little bit quick, actually, and then Thursday's lecture, these two lectures probably be like half lectures. So the lecture we're doing today is semi-interesting, but I think the lecture we do on Thursday is going to be more interesting. I think most people will like the lecture that we do on Thursday. But today we're going to do a little bit more optics. Like I said, this is extra credit simply because we're running out of time, and I can't, have a homework or quiz on this. But it's semi-important for optics. What I'm trying to say is that this stuff isn't sort of not important. It's just that we're running out of time, so that's why it's extra credit. So what we're going to talk about to start with is the diverging cases of mirrors and lenses. So on your test, the non-extra credit portion of the test will be on converging mirrors and converging lenses, which of course we did already, and it's on the homework, and it'll be on the quiz too on Tuesday. So this is where the light focuses the image, basically, for either the diverging mirror or the diverging lens. And you should, converging mirror or converging lens, which you should know how that works pretty well for the test. But this is the opposite case, and actually I was going to try to bring in a mirror that looks like this, but it's missing. We have a demo room where these things are supposed to be, and someone took it and didn't put it back, so I don't have it. But it's basically, like a Christmas ornament, right? So basically, if you look at a Christmas ornament, it's, like a metal ball, and the light rays hit it from the outside. So if you coat the inside of this thing with, some sort of reflective material and shoot rays in on this side, it's a converging mirror. But if you look on the other side, right, so this side's mirrored here, and you shoot light rays in parallel to the optic axis, it becomes a diverging mirror. So basically, if you're looking on the outside of the mirror instead of the inside of the mirror, it's a diverging case. And for this case, it just works on reflection again, just like the converging case does. But when you send in light rays, they come in and they bounce off with respect to the normal. So this case here, the normal is like in this direction here. But the angle comes in with the angle comes out with it is the same with respect to the normal. But all the actual light rays sort of bounce off, just like this. And they don't actually focus, right? So what happens is if you extend the reflected rays, kind of like we do when you put an object inside the focal point of a converging mirror, these virtual rays, the same thing as we talked about when we form a virtual image, actually do cross, and they form a focal point actually behind the mirror. So we actually call it a virtual focal point. And anything virtual, in other words, if you get a image that's virtual, the image distance should be negative for a converging case, right? We went over this. And you should know it pretty well for the test next week, that if you put something inside the focal point, you get a virtual image that has a negative image distance. Because this is a virtual focal point, just like the analog of a virtual image. The focal point is actually negative, right? So it's a little bit weird. You have a negative focal point, but this is the case for diverging mirrors because they have a virtual focal point. Mathematically speaking, their focal point is also negative. It's half the radius of curvature, but it's negative half the radius of curvature. And everything else is the same. So it's the same lens or mirror equation for converging or diverging mirrors or lenses. However, for diverging mirrors at least, the focal point is always negative. That's the difference between converging cases and diverging cases. The math is the same. You just got to remember that the focal point is negative. A diverging lens is the same thing. So here's a converging lens. If you send in, we already went over this, right? If you send in light parallel to the optic axis, it focuses on the opposite side that it's sent into, and all the rays actually focus. Here, if you send in, this is a diverging case, by the way, where the lens is shaped opposite, right, of this case here. So this, curves outward. Here it curves inward, and that forms a diverging lens. And for a diverging lens, if you send in light parallel to the optic axis, it bends due to refraction, of course, not reflection. But because of the shape of the lens, it actually bends away from the optic axis and not towards the optic axis. So all the actual light rays bend away on this side here. So once again, they don't form, they don't converge to form an actual focal point. So if you extend the refracted rays like this, they form, once again, a virtual focal point where the focal point is negative again. So just like a diverging mirror, a diverging lens also has a negative focal point. But everything else is the same. You still use the same equations. The only difference here is that f is negative. If you look at the magnification, just like it's basically an analog of a virtual image for a converging lens or converging mirror. If you put something inside the focal point, you get for the converging cases, you get a virtual image with a negative SI. But if the image is negative, in other words, it's virtual, when you plug it into the magnification equation, you get a positive answer for the magnification, meaning the image is upright. So this is always the case for diverging lenses or mirrors, is no matter where you put the object, because the focal point is negative. I should say, okay, so if the focal point is negative, I skipped this part. If the focal point is negative, the image is always positive, right? So what am I trying to say here? No, okay, so if SI, right, if F is always negative, okay, yeah, sorry, all right, I forgot about this step. Okay, so if you look at the denominator, right, you have SO minus F, but F is a negative number, so this is a positive number because SO minus a negative number gives you a positive number all the time. You're adding F to SO basically. But because F is negative, this is always negative, right? The numerator is always negative. So you're always dividing a negative by a positive, which gives you a negative image distance, right? So SI is always negative just like it is for putting a object inside the focal point of a converging lens or mirror. So for all diverging mirrors, right, it doesn't matter where you put the object, right? You could put it wherever you want. The image is always negative, which means that you always form a virtual image, like all the time, right? For any case of diverging lens or mirror. And then because SI is negative, the magnification is positive, just like the case of putting something inside the focal point of a converging lens or mirror. Anyhow, to summarize, the only difference between diverging lenses and converging lenses, or diverging mirrors and converging mirrors, is that the focal point is negative. That's one difference. And because the focal point is negative, you always get a virtual image. And because you get a virtual image all the time, the magnification is always positive. It doesn't matter where the object is placed. That's the idea for these diverging cases. All right, so let's do a simple example of the case of diverging lenses or mirrors. Okay, so it really doesn't matter which case you use, either diverging lens or mirror. It doesn't really matter. It's the same math for either case. For both of them, they have negative focal points, and they use the same equation. So it's really the same question, whether you put something in front of a diverging mirror or diverging lens. It's the same thing. So here we're doing a diverging lens with a focal point of negative 40, right? So for any diverging case, whether it's a mirror or a lens, the focal point is always going to be negative. In fact, if it's not negative, if you're asked to find the focal point of a diverging lens or mirror, and you don't get a negative answer, it means that you've done something wrong, because it's always negative for the diverging cases. Okay, so it's the same sort of question we can ask for a converging case. For instance, what's the image distance? So for converging lenses or converging mirrors, or for any situation of a lens or mirror, you always have this equation, right? 1 over SI plus 1 over SO is equal to 1 over F. So it's the same thing. The only difference here is F is negative. But besides that, it's the same. So 1 over SI, which is the thing we're trying to find, the image distance, well, not 1 over SI, but SI, is equal to 1 over F minus 1 over SO. So then you plug in what we know. So this is minus 40. That's the focal point. So the negative is, really important when you're talking about diverging lenses or mirrors to, actually plug in the negative there. And then SO is always positive for what we're doing. So this is 20 because we're putting the object 20 centimeters in front of the lens. So if I can get a common denominator easily, like I said, I try to do this just with arithmetic if I can. And yeah, this is easy to find. It's just 40, right? So it's basically minus 1 over 40 because it's 1 over negative 40, which is the same thing as minus 1 over 40, minus 2 over 40. So 1 over SI, not SI, but 1 over SI, is minus 1 minus 2, which is minus 3. And then this is over 40. So SI, you got to remember on the test for either case of converging or diverging cases to take the inverse, right, at the end, right? Some people forget that. So that's the answer, right? It's minus 40 over 3, but the fact that it's negative also means that it's virtual, just as the case was the case for converging cases, right? Whenever you get a negative SI for anything, it means that the image is virtual. And you should always get a virtual image 100% of the time. If you're talking about a diverging lens or mirror, right? It should always be virtual. It's never real. Okay, so that makes sense that it's virtual. Okay, so then B, what's the magnification? Okay, so magnification is the same thing, whether you're talking about the converging cases of both mirrors or lenses or the diverging cases. It's still minus SI over SO. The difference is that for any case of diverging lenses or mirrors, the image distance is always negative, right? It's always virtual. That's the only difference between the converging case and the diverging cases. So it's minus, because there's a minus in the equation, but it's minus 40 over 3, which is, of course, positive 40 over 3, divided by 20, because that's where we put the object. So the units cancel out, as they always do for magnification, and the 20 and the 40 make it 2. So the magnification is positive 2/3, or like 0.67. But the fact that it's positive, of course, means that it's upright, right, for any case, whether it's converging and diverging cases, right? If you get a positive answer for the magnification, it means it's upright. However, for diverging cases, it's always upright. There's never a case where it's not upright. Okay, so then that's pretty much it. I mean, you can draw a ray diagram, but we're not going to do it for diverging cases. For converging cases, we might have to do it, but not diverging. So that, those are the basic things you can do with diverging mirrors or lenses. It's really not that much different than the converging cases. All right, so does everyone, that make sense? It's not too bad, yeah. Yeah, they always look like, you're talking about mirrors, right? It's like this, right? So you're looking at it from this side. Yeah, it's like a Christmas ornament. It's like this. This is a converging. My cup is basically converging. Sorry, diverging mirror, right? I mean, it's not the best mirror, but it does reflect things in sort of form of mirror. Okay, so that's diverging cases of both lenses and mirrors. So it's not so much different than the convergent case. All right, so the next thing I want to talk about is polarization, which is another, oh man, I should look for the polarizers. All right, next class, I'll bring this stuff next class, see if I can find it. All right, I'll bring you a diverging mirror and this thing, which is a polarizer, and I'll show you what these things look like. But, okay, so when you produce electromagnetic waves, it's basically created more or less, although, to really understand it, you need to know a fair amount of quantum mechanics. But more or less, it's produced by an oscillating charge, usually an electron in the atom. So when electrons are in atoms, they're moving basically in all different directions. They're not just moving all in the same direction, typically. So basically, light in this room, all the electrons are moving in all these random directions, and they're producing this light that you see, in this case, visible. When they produce electromagnetic wave, remember, there's this like right-hand rule for electromagnetic waves, and they travel in a certain direction. If the electric field's in one direction, magnetic field's in another direction. The point is, if these electrons are in all different sort of directions, one's oscillating vertically, and one's oscillating horizontally, one's oscillating at an angle, one's going this way and that way, they produce the electromagnetic waves that go like in all different directions, that have all different sort of combinations of which way their electric and magnetic field is going. This is known as non-polarized light. So basically where the electromagnetic wave produced by the electrons are in all sort of random directions, which is actually the case from these lights. So what you can do is create a material which is known as the polarizer, which I'm going to bring in next class and show you what that looks like. That basically limits, so basically when unpolarized light, when light coming from this, these lights here passes through this thing called the polarizer, it forces light to basically oscillate in one specific direction after it passes through the polarizer. That's what polarizers do. It basically forces light just to move in basically one direction and filters out all the other directions. And therefore the light is less bright because you're losing a lot of light because there's all this light coming in, vibrating in all sorts of different directions. And then when it passes through the polarizer, it's only going in one direction. So you lose all the light that was vibrating in all these other directions. So intensity of light is basically related to how bright the light is. We're not going to get into a calculation of intensity, but you can calculate the intensity. But basically intensity, which is this I thing, is related to how much light, how bright the light is. So basically what we're saying here is if you take unpolarized light, which is represented by this symbol here, it's basically light going in all different directions. When it goes through a polarizer, it's basically just going in one direction. And when you measure how bright the light is here, it's a lot less bright than this light because you lose all these other directions. And what we're saying here is that if you take unpolarized light, put it through a polarizer, the amount of light left by intensity, or basically how bright it is 1/2 what came in. So basically you lose half the intensity of light. So you have polarizing sunglasses, which do this, right? So they have polarizers on them, and when the light passes through, half of it's gone, and that's part of the concept of these polarizing sunglasses, right? Part of it. There's another reason behind polarizing sunglasses, but I won't get into that right now. So then the question is, what happens? Oh, by the way, so each polarizer has what's known as a transmission axis. So it's basically the direction that after the light passes through the polarizer, how it's polarized after it goes through. In other words, in this case here, the polarizing axis or the transmission axis is vertical. So basically what that means is that when you have unpolarized light passing through it, when it comes out, it's only vertically polarized. So the transmission axis here would be vertical, right? You could also make it horizontal if you rotate this thing. So the transmission axis is horizontal. And if that were the case, then only horizontal light would come out instead of vertical light. So the question is, what happens if you have already polarized light like this, and then you put another polarizer after it? Well, then it behaves a little bit differently. So suppose you have unpolarized light, and this is, say, a vertical transmission axis, basically like what we have here. So basically, after it passes through the first polarizer, which is this rectangle here, it's vertical, and then you have another polarizer after it where the transmission axis, or how it polarizes the light, is not vertical. It's like this. It's at some angle with respect to the first one. Well, the idea is that after it comes out of this second polarizer, it's going to be polarized in the direction of this polarizer, how this one's orientated. So it would be like diagonal like that. But of course, you would lose some of the light because, the light isn't, it's it was originally perpendicular and it comes out sort of diagonal. So you lose some of it. And the idea is if you have already polarized light and you pass it through another polarizer, the amount of the intensity of the light, or basically how bright it is, after it passes the second polarizer, is equal to, is given by this equation here. It's the intensity that you had before you went in there, so it would be the intensity of this vertical light, times the cosine squared of the angle between the two transmission axes. The cosine squared is just the cosine of the angle, and then you square it, right? But mathematically speaking, you always write it like that, cosine squared theta. But you just take the cosine of the angle and square it, and multiply it by the original intensity, and that gives you the intensity after it's gone through both of them. By the way, if the angle is 0, what do you think you get? What's the cosine of 0? In other words, if this was vertical, so that the angle between them is 0, what's the cosine of 0? 1. So you don't lose anything, which makes sense. However, if it's horizontal, right? So this one's vertical and this one's horizontal, so the angle is 90 degrees. What's the cosine of 90? 0. So no light gets through, right? If you have what's called cross-polarized polarizers, where they're basically the transmission axes are 90 degrees apart, you get no light going through at all, right? The intensity is 0 after it goes through the second polarizer, which is something kind of interesting to show. So I'm going to do an example with polarization in a second here, but let me just give you an example of polarization, practical example. So if you go to a movie theater, I actually have a 3D camera here. We used to make these things, now I don't make them anymore. But anyway, so the question is, how do you see in 3D? Like before, so how do you, right now you're seeing in 3D. The question is, why do you see in 3D? Right now. Like we clearly see depth, right? Three-dimensional objects we see. We don't see a 2D thing. When you look out in front of you, you see 3D. So the question is, why do you see 3D? And not 2D. No one knows? No one knows why you see 3D and not 2D? It has to do with your eyes. It's because you have two eyes, right? That are spread out. You get two different images, one from the left and one from the right. If you close your right eye, you see a different image than your left eye. Your brain puts that together and it forms a spatial image, right? It forms depth. If you lose sight in one of your eye, you lose depth perception, right? It's a big deal. So when you watch a 3D movie, for instance, right? You go to the theater and there's 3D movies there. So how do they make 3D movies? They make 3D movies using cameras with two lenses, which simulate your two different eyes, and they get two different pictures. That's what I have here. This is actually 3D camera. So if you, yeah, it turns on. But if you look, there's two different lenses, right? That are basically typical human eye width apart, right? And it takes two different images, right? Okay, so one is the image from the right, and one is the image from the left, which simulates your right eye and your left eye, correct? So then what you need to do is get these two images. So when you're watching the movie, you want the picture that was taken from the right lens to go to your right eye, and the picture that was taken from your left lens to go to your left eye, right? So when you get to a movie theater, what do you put on? Typically you put on glasses, right? Those are polarizers, right? So those two little pieces of plastic are actually polarizers. So when you get to a movie theater, the screen, or the reflection from the screen, is polarized, so that basically the left side, the left image, right, from the left lens, is, say, polarized, well, in this case here, vertically, right? And then the right one is polarized horizontally. So basically, on your glasses that you wear, the left side has a polarizer, which is vertically polarized, although the picture here is backwards, by the way, but whatever. Okay, so it's vertically polarized, right? So basically, only the vertical light gets through, the horizontal light doesn't get through at all because it's 90-degree angle with the polarizer. So basically it filters. What I'm trying to say is it filters the image so that the left image goes to your left eye and the right image goes to your right eye, right? And then your brain basically sees that as 3D, just like you're looking at here, right? Otherwise you see 2D, right? Alpha image, you see 2D, not 3D. All right, so does that make sense, how that works? By the way, this screen has this doesn't require any glasses. The screen is 3D itself, which is more complicated to explain how that works than the glasses work. But you can get 3D screens, but you can't get gigantic 3D screens yet, right? Although they're working on it. They have something, they're trying to develop screens that are 3D without glasses, but they haven't gotten that far yet. Okay, so let's go to an example of polarization. Okay, so I'll draw a sketch too that goes along with this. It makes it a little bit easier to understand. But okay, so unpolarized intensity is measured in power, so power is watts, per area. It's basically how much power the light has per meter squared, right? That's what intensity is. So the bigger the intensity, the more power per meter squared, which means it's a brighter light, basically. Anyhow, so it's 10 watts per meter squared is the typical units for intensity. It then passes through a polarizer. Okay. So after it passes through the first polarizer, it then passes through a second. Okay, the transmission axis, which is basically what direction it polarizes the light, which is TA for short, is 30 degrees relative to the first. It actually doesn't matter what the actual axes are, just what matters is the angle between them. The question is, what is the intensity after the second? I'll just type it out, polarizer. All right, so this is actually not too hard. You just have to do it sort of step by step. So we represent unpolarized light when we're, as symbolically as basically this sort of star shape thing. I'll show you in a minute what I'm talking about. So you draw, a vertical one, and then you draw a horizontal one, then you draw two at approximately like a 45-degree angle. It doesn't have to be perfect. It's just a symbol to represent unpolarized light. So this just means that the light is basically, oscillating in all sorts of different directions. So you represent that by just drawing light, sort of going in every direction. So that's unpolarized light. And this intensity is given, right? So I is intensity. So this is the initial intensity or the original intensity. And this is 10 watts per meter squared. Okay, so then that passes through one polarizer. It doesn't matter the orientation of the first polarizer. It can be any sort of orientation, but let's say it's vertical. It doesn't. You could draw it horizontal if you wanted to. It actually doesn't matter at all. So this is the first polarizer, but let's say the transmission axis is vertical, right? It's kind of like how I drew it. So in other words, what this means is that it only allows light that's going vertical to pass through it. So it's going to be a little bit confusing, but I'm going to do the arrows in orange. So what this means is, light, this isn't an arrow related to the light. It's just an arrow saying it's going through the polarizer. So after this unpolarized light goes through this polarizer, what happens is it comes out polarized. That's the whole point of this thing, meaning that it only is now sort of oscillating in one direction and not every single direction. And this direction would be vertical because that's what the polarizer is. It's vertical. So it gets rid of all these other things and only leaves the vertical one. So the point here is that when you take unpolarized light and pass it through any polarizer, it doesn't matter what the orientation is, it can be anything, then the idea is you lose half the intensity, right? So after it passes the first polarizer, which I'm going to call I1, intensity 1, it would be half of 10. So the intensity after the first one is 5 watts per meter squared, right? So this light here would be half as intense or half as bright as the original light that went in. All right, that's pretty, I think, straightforward. But now it goes through another polarizer. So we have another second polarizer. And that is not vertical, right? Because it's at some sort of, although, okay, so I'm just going to draw it in the same way as I drew it before. Oops, okay. But this one is angled, right? So it's not vertical. It's at some angle. So it's like this. Right? So if you measure the angle with respect to the first one, which was vertical, it's not to scale sort of at all. But the point is that this angle here, this angle here, if I can draw it in, that angle is 30 degrees, right? Okay. So the point is, once you send the already polarized light, which is what it is after it's gone through the first polarizer, through the second polarizer, then it's also polarized, but it's polarized in a different direction, which would be the direction of the second polarizer. So in other words, after it comes out of the second polarizer, it's basically in the same direction. It looks like that, right? So it changes the polarization. But of course, you also lose some light. So originally it's 5 watts per meter squared. And then after it goes through the second one, it's not going to be 5 watts per meter squared anymore. It's going to be less than that because you lose some light. So the question is, what's the the final intensity after it goes through the second one? So that's this. That's the second equation, which is I2, which is the second, after it goes through the second polarizer, is equal to I1 times the cosine, actually it's I1. Yeah, I1 times the cosine squared of theta. So it's 5 watts per meter squared times the cosine squared of 30. So it's the angle between the two polarizers goes here. Now, cosine squared is the cosine of 30, and then you square it. Right, that gives you cosine squared of 30. So anyhow, that turns out to be, I think, 3.75. Yeah, so it's 3.75 watts per meter squared. And that's how polarizers work, right? It's pretty straightforward. I mean, it might be a little not straightforward. You got to understand whether the light is polarized first, right? Because if it's not polarized, it's always half, right, after it goes through any polarizer. But then if it's already polarized, and then you have to use this equation here, right? That's for if it's already polarized. So you start out with 10. After the first one, you have 5. After the second one, you're left with 3.75. All right, so does that make sense? Okay. So the last thing I want to talk about today, actually, and then we're not going to take a break. I'm going to just go through this last concept and then do an example, and then you guys can go. Is constructive and destructive interference of light waves. So basically any sort of wave, it could be a sound wave, it could be a water wave, in this case light wave, can experience this thing called destructive and constructive interference. So if you have any two waves which are the same amplitude, the same height, and the same wavelength, which is the same distance between crests, if they're basically lined up so that you have two light waves, right? Two light waves coming in, and they're the same wave, but they're basically lined up so that basically each crest is over a crest and each trough is over a trough. This is the trough, by the way, the lowest point. The crest is the highest point. But anyhow, if they're basically lined up perfectly, then what happens is they just add together and you get a wave that's twice as high. If it's a water wave, it's literally twice as high. If it's a sound wave, it's louder. If it's a light wave, it's brighter, right? So basically, if the amplitude gets bigger, if the height of this thing gets bigger, that relates to how bright the thing is. So you get a brighter, the light, when you combine these two waves, would be brighter than the individual light that you sent in. If the light is completely misaligned, by the way, this is called constructive interference. You can see it right there. But if the light is misaligned, so that basically a crest is over a trough, like just like this, here's a crest, here's a trough, then this is known as destructive interference, and basically the wave completely cancels out. So if it's a water wave, you don't see the water wave. If it's a sound wave, you don't hear anything. If it's a light wave, you cancel out, and if you don't see any light, it becomes dark, right? So it would be two light waves come in, and if they align like this, they basically turn to black, and you don't see anything, right? That's the whole point of destructive interference. So that's conceptually what constructive and destructive interference are. Now, what you can do with light is do this thing called a two-slit interference or double-slit interference. So it works like this. It's actually not so hard to understand what's going on here. Okay, so if you take light and you shine it through two slits, so this is a single, say, laser light that's shined through two tiny little slits which are separated by some distance, right? So there's a hole here, and they're separated by a distance of d. Then what happens is they go through these two slits, and it's the same light wave, basically, because it's the same laser passing through both of them. So it's exactly the same wave. However, if you have a screen over here, they travel different distances to get to a single point of the screen, which I'll explain in the next slide here. Okay, so here. Okay, so suppose you have a screen here, right? So you take two, you have a little screen with two little, this side over here, you have a little screen with two little openings in it, and you shine light through it. Then you have another screen on the other side here, and you pick a point here, and you're trying to figure out what's going on at that point from those two sources of light, from the two slits, right? So basically what's going on here is that if you look at this point here, this light, the distance from this slit to this point is going to be less than the distance from this slit to this point, correct? Because if you just look at it, this one has to travel some extra distance to get to this point. Okay, well, if it travels an extra distance, you can picture this light waving, it's going to end up at a different point than this slit here at that point, right? In other words, so this light's doing this, right? So it might land at this point when it gets to that point. But this one has to go further, so it's got to go wave a little bit more, and it might land on that point when it gets to the slit, right? So what we want to do is figure out what is the difference of distance. How much further does the second does it have to go to get to the point in the second slit as opposed to the first slit, which is what we're doing here. So basically what happens is if you draw a triangle like this, right? So basically this is one side of the triangle D. This is theta, which we'll get to in a minute. We'll understand what theta is in a minute. Let's just call that theta for now. And you make a right angle here. The extra distance that this second one goes to get to that point is this side of the triangle. It's by geometry. It's a concept of geometry. So if you want to figure out this side of the triangle, it's basically, so this is the right angle. This is the hypotenuse of the triangle. This is, if you call this theta, which we'll get to in a minute what theta is, but if you call that theta, then this side is the opposite of theta, so it's going to be sine. So it's d sine theta, is the length of this side here, right? That's d sine theta, which is the extra distance that the light has to go from the second slit to get to the point on the screen, correct? Okay, so if that distance is exactly equal to a multiple of a wavelength, say it's one wavelength, right? So suppose this, to get to the point on the screen, this light goes this far and it ends at this point here. If this goes one extra wavelength, right? So this is here and it goes one extra wavelength, then it also ends at the same point, correct? Because it ends at the same point, it basically reinforces one another and you get a bright spot, basically. It constructively interferes and you get a bright spot. So what I'm trying to say is that if the distance, extra distance that this second ray has to go, or second source of light has to go, is equal to a wavelength, or two wavelengths, or three wavelengths, or four wavelengths, it doesn't matter as long as it's a multiple of a wavelength, then you get a bright spot on the screen. That's the point, they constructively interfere. So this is what we're doing here, right? So the extra distance that it goes, d sine theta, if that's equal to a multiple of the wavelength, which is 1 or 2 or 3 or 4 or 5, or actually 0 works too, as you'll see, then you get a bright spot. Actually, negative works too. I'll explain negative when we do an example what negatives mean, but also negative numbers work too. -1, -2, -3. Okay, so if you go back to this picture here, we measured some angle here, theta, right? This is theta. Well, if you draw a line from the middle of the two slits, right in between them, like right here, and you draw a horizontal line to the screen, which is this here, then theta is also the angle between the middle, right in between the middle of those two slits to the point and this horizontal line used through. This theta here is equal to that theta. So basically, these two thetas are the same, and we can use that to figure out the rest of it. Okay, so this theta is the same as that theta. So we have this equation here. The d sine theta is equal to m times lambda, where m is some number. And then what we typically do is say that we solve for theta, which gives us what angle this needs to be to see a bright spot, which I'll explain how that works in a second here. But if you solve this equation for theta, you get the inverse sine of m lambda over d. And usually we characterize that by m. So in other words, m can be anything. It can be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It can be -1, -2, -3, -4, -5. So basically what you do is you label the theta by your m that you choose. So instead of saying theta, you say theta sub m, where m is whatever value you pick for m. It could be 0, 1, 2, 3, 4, 5, 6, or whatever. So in other words, if you pick m to be 0, you can say theta 0, which is the theta for your m chosen to be 0, is 0 degrees. So it's actually right in the middle here. You see a bright spot. But theta 1, which would be the first spot that you see, is 1 times lambda over d. Theta 2 would be, well, the inverse sine, I should say, of 1 times lambda over d. Theta 2 is the inverse sine of 2 lambda over d. And that gives you a bunch of angles, which you can use to figure out where all the bright spots are on your screen, right? It's called two-slit constructive interference. So this is the last thing I'm going to do today, and then you guys can go. That's why there's no breaks. But what we're going to do is do an example of calculating these angles for our two-slit interference. Okay, so let's go to here. Okay, so the other thing I didn't point out, but I'll point out now, is that well, you'll see it when we do the calculations, but the size, the distance between the slits has to be somewhat close to the wavelength of light, or else you don't see anything. So if the wavelength of light is 500 nanometers, which is a typical sort of wavelength of red light is around 500 nanometers, that's pretty small. So basically, the distance between the slits has to be pretty small for you to see this effect. Passes through a double slit separated by 4,000 nanometers. So something like that, right? So 4,000 nanometers is 4 billionths of a meter, right? It's pretty small distance there. But anyhow, determine 5 angles where bright spots appear. Okay, so that's just using the equation I just went over, which is this equation here. It'll be on your equation sheet. Even the extra credit stuff that we do today and tomorrow will be on your equation sheet when I post it. So this equation will be on your equation sheet. You just have to know how to use it if you want to get the extra credit questions correct. So theta m is equal to the inverse sine of m lambda over d. So it's basically you can just choose n to be whatever you want, but you usually start from m equals 0 and then go to m equals 1 and go to m equals 2. So let's just start with m equals 0 and see what we get. So if m is equal to 0, that means that theta 0 is the inverse sine of 0, because m is 0. We just chose it to be 0. Lambda over d. It doesn't matter what lambda and d are because the inverse sine of 0 is always 0. So that means the first spot is at 0 degrees. And when we're done with this, I'm going to draw a sketch that puts this all together and makes more sense. But the first angle is 0 degrees. It's always 0 degrees, actually. It doesn't matter what the wavelength or distance are between the slits. That's sort of a trivial one. The first non-trivial one, we're going to choose m equals 1. So m equals 1 gives you theta 1, which is the inverse sine of 1 times lambda over d, which is the inverse sine of just lambda over d. Okay, so as long as the wavelength and the distance between the slits are the same unit, they could both be meters. They're not going to be meters because it's going to be a pretty small number. But if they're both in meters or nanometers, it doesn't matter. They just have to have the same units, so the units cancel out. So if they keep them both in nanometers, it's fine. So the wavelength is 500 nanometers, so just leave it like that. The distance is 4,000 nanometers. So they cancel out. That's what you want to have happen. And when you do that, you get plus 7.18 degrees. So that means the next spot you see is at 7.18 degrees. And then you do the same thing for m equals 2. You just pick different m's. That's all you're doing. It's not really, it seems like it's hard, but it's not hard. You're just picking different m's, right? So you can pick m to be whatever you want. But typically you start from 0 and you just go up from there. So m equals 2 gives you theta 2, right? It's the theta for m equals 2. So it's 2 times lambda over d. Well, inverse sine. I keep on forgetting about the inverse sine. But so all you do is you just multiply this by your numerator by 2, which of course gives you 1,000. So it's 1,000 divided by 4,000. And that's theta 2. And then you take the inverse sine of that. And that gives you your next angle, which is almost double your first angle, but not quite. So it's 14.48. And it's positive. So that's another one, just choosing m to be 2. But you also have negative ones. So if you chose m equals minus 1, it was on the PowerPoint. I didn't really mention it on the PowerPoint, but I'll mention it here. If you choose the negative of something you already calculated, right? So I already calculated m equals 1. M equals negative 1 works like this. That'd be theta negative 1 because m is minus 1. But that's just minus theta of 1. So basically, if you found theta for m equals 1, it's just the negative of it. So if you found the positive ones, you also found some negative ones. You could do the same thing for m equals 2. So, minus 2, right? So m equals minus 2 is theta minus 2, but that's minus theta 2, which is negative 14.48. So these give you 5 different, I'm going to box all these at once, but I'm going to draw a sketch, and it makes it easier to see. But these give you 5 different angles. You get 0, positive 7.18, positive 14.48, negative 7.18, and negative 14.48. So what does this mean, though? So, oops, sorry, I did the wrong thing. So, you know, you can calculate these things fairly straightforward. You just pick different ends, but what does it mean in the end? Okay, so let's draw a sketch of what this looks like when you actually do sort of this experiment and see what it looks like in person. So what you have here is, say this is the screen or whatever it is with two little holes in it, right? So this, you're shining light through these two holes, which are separated by whatever it was, 4,000 nanometers or whatever. And then over here you have a screen where you're trying to figure out where the bright spots are. Okay. So what we just calculated is, first thing you got to do is draw a horizontal line that goes through the middle of these two slits to the screen. So it's like this. Should be in the middle. I didn't get the middle perfect. All right, I got to do that again. It should be in the middle. I have it in the wrong. Stuck on my eraser here. But to get it perfect or make it look better, it should be exactly in the middle of these two things. All right, that's better, but it's still not in the middle. All right, let me slide this down a bit. Okay, that's pretty good. Okay, so now what we did is we found that one of those angles was 0 degrees, right? The first one we did was 0. That means a bright spot happens right here where that line intersects the screen. So if you look straight in front here, you'll see a bright spot. And then we figured out 7.18 degrees is where the next one happens. So that would be this. If you draw a line that's at a 7.18 degree angle from that horizontal line, like this, that's where another bright spot will be. And that's the m equals 1 bright spot, right? Then we found another one for m equals 2, which is 14.48 degrees. So basically, if you draw a line from the middle here to the screen, so that this angle here, that would be another bright spot. So that's m equals 2, right? And then we have the negative angles. So it's the same thing, but now you're going below that horizontal line. So in other words, well, it should be symmetric. I don't know how symmetric you're going to draw it, but it should be symmetric. So this is 7.18 degrees below the black line. That would be m equals minus 1. And then 14.48 degrees below it, that would be m equals minus 2. So basically, these are all the bright spots up here. And you can keep on going. You can do m equals 3, m equals negative 3. And that gives you all those other angles. And those were, I didn't do the same color, but you get the idea. And those tell you exactly where all the bright spots are, right? That's what we're doing here. That's what these angles are. So that's basically how it works. It's really not too hard to figure that out, right? By the way, one more thing. The brightest one is m equals 0, and then m equals 1 is less bright, and then m equals 2 is less bright. Same thing for m minus 1 and minus 2. Does anyone know why they would get less bright? So they're definitely bright spots, but the question is they get less bright the bigger the m is. Does anyone know why they would get less bright? Anyone have a guess why they would get less bright? Anything? Do you see anything in the picture that would indicate? I mean, you can see it in the picture, basically, if you look at the picture. Yeah. Right. So, you know, the light blue one has to travel farther than the purple one. And when things travel farther, they get less bright, right? I mean, we know that. If you put a candle further away, it gets less bright, right? Same thing. So that's why they get less bright, right? Because they have to travel further. Eventually, you don't see them anymore because they're not bright enough to see, right? So after some point, you can't see them anymore. But they're there if you could somehow detect them, right? You can keep on going to m equals 1,000 or whatever, and they'll be there. All right, so that's today's lecture on the optics portion of the test that is extra credit. On Thursday, we're going to do some interesting stuff on modern physics, some stuff on relativity and quantum mechanics, which would be sort of interesting, I think, for most people. So that's what we're going to do on Thursday. All right? All right, so I'll let you guys go early today. Probably early on Thursday, too, a little bit earlier.